Hi everyone, welcome to this presentation on inferential statistics. In this video, we're going to talk about Run's test. The Run's test is also known as Run's test for randomness, and it is one of the non-parametric statistical tests used in inferential statistics. The objective of this Run's test is to primarily, the objective of Run's test is to assess the randomness of a sequence of observation. That means if we have a sample of data, then whether the sample is random or not, that check we can do using a runs test. It determines whether the elements in the sequence are randomly distributed or they exhibit some pattern. And it has a lot of applications in the field of quality control, finance and economics, genetics, bioinformatics, psychology and behavioral sciences, and telecommunications, for example, and signal processing, and gaming, and environment sciences, to name a few. So let's get started and see how this runs test is configured and how it is used in Python, and also understand the step-by-step details of runs test. So a little bit of prerequisite knowledge about Python and basic probability and statistics would be useful, and some elementary idea of data science and machine learning would be really handy. So runs test is also known as Wald-Wolfowitz run test, and this is a non-parametric statistical test, as we discussed or as we talked about it earlier in the introduction. Used to determine the sequence of data points in a sample is randomly ordered or not. And essentially, we will test the null hypothesis. So the null hypothesis is going to be the sample is randomly, distributed. And we will test the hypothesis. And if it is not true, then we will go with the alternate hypothesis. So why we look for random sequence? More for statistical validity. Many of these statistical analysis, the randomness or characteristics of randomness is fundamental assumption. In quality control, when we look for any production processes, and we need to check the randomness uh, of data in the quality control evaluation methods. Many of the machine learning, deep learning algorithms also require data to be randomly initialized, at least. Market analysis, let's say stock market, is called stock price movements. We would like the data to be randomly spread. And likewise, simulation and modeling techniques used in operations research also make an assumption that sample data is randomly distributed. So, for example, runs would be, let's say, what would run mean when we toss a coin? So let's say the series of events like head and then tail, tail, then head, head, then tail, 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 then head, and then tail again. So a sequence of tosses of a coin, and if the toss is same in a sequence, that would be one run. For example, here, so starting with heads, so this is one run, this is one run, another run, another run, another run, and a total 6 number of runs here. The first one is with the length 1, second one length 2, 3, and 1. And this is how typically the data is when you toss a coin. We would like to see if the events are actually random, or the tosses or the coin landed randomly. So that we can check using Run's test. Let's see another example. A data scientist carrying out some research and they interviewed 10 people, and the genders of those 10 people are men and women. And if the runs are like, let's say the first patient is male, 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 male again. So this is a run of one, or first run, and then female, female, female. So this is a second run here. So in this series, we have two runs. And likewise, the other examples also. All right, so let's see here one more here. So if the sequence of numbers have very few runs in the sample, then it is likely that it is not a random sequence. For example, here, if you look at it in the series here, the values are increasing in order, right? They are in one direction, and that's non-random. So this is a run of one, okay, in the increasing order, up run. So this is not likely to be a random sequence. All right, so the features of a run essentially is characterized by two attributes. One is the number of run and the length of run. The up run, the sequence of numbers, each of which is succeeded by a larger number. Down run would be succeeded by a smaller number, for example. So two things, the number of runs and also the length of runs. These two characteristics are used by the statistical test called runs test to determine if the sample is random or not. For example, here again the random walk theory, and in this random walk theory, um, it's also a runs test here. For example, consider the following combination of upward and downward price movement. So this is a run of 1, 2, 3, 4, 5, and so on and so forth. So there are 7 runs here and total of 12 observations. Okay, all right. So now let's see how we put all these things together. And likewise for stock price data also, run can be considered in terms of the number of times the prices are increasing in succession and the number of times the prices are going down in succession. So one succession is one run. So for example, here plus means the price increase, the negative means the price decrease. So that's how we identify the runs, plus and minus, minus, plus, 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 and total number of runs is 10. Now, once we determine the runs, now we have to count the number of increases and decreases. So number of increases, the number of runs which were in one direction versus the number of runs which were in the other direction. So count those runs and call them N1 and N2. And after that, we compute the mean of the runs and the variance of the run. And this is the statistical formula that we use here. The expectation for the mean of run is 2 times n1 multiplied by n2 divided by the sum of the number of samples or number of runs in each. And that gives you the mean run. And similarly, substitute the value in this formula, and that will get you the variance. Now, these two will be utilized subsequently in our exercise. And after that, we compute the z statistic or test statistic and critical value. For a two-tailed test, we know that at 5% significance level, the z-value is plus or minus, depending on what tail we are talking about, 1.96. So with the data that we obtained in the previous step, like a mean of the run and the variance of the run, we utilize that here and substitute the values and we get the z-score or z or rather test statistic. So why we use a standard normal distribution for critical values in this runs test? The use of standard normal distribution is coming from the theory of central limit theorem. And this suggests that for large sample, the properties actually tend to be approximating to a normal distribution. So central limit theorem says that the distribution of a sample mean or sum of a large number of independent and identically distributed variables, they tend to take the shape of a normal distribution. So in the context of runs tests, the number of runs is a sequence and is treated as a random variable. And we are talking about large number of samples here, more than 50, 60, or 100. So when the sample size, the number of observations is large, then the distribution of the number of runs can be approximated by a normal distribution. And that is why we consider normal distribution as a reference in the runs test. So the approximation for the large samples, the exact distribution of number of runs becomes very difficult to compute. Exact means exact, so we go with the approximation. And in order to get the approximation, we have the mean and standard deviation of the number of runs that we derived in the previous step, and that can be utilized to get the distribution. So once these parameters are known, you can plot a distribution, and that will help us determine the critical values and p-values for the alpha level. So let's take a look at the Python code and see how we develop the runs test. Okay, so this is a little Python piece here, and I'm taking a data sequence randomly. And in this data sequence, okay, let me first get you the problem statement as to what we are trying to solve here. The problem statement is that this is actually the blood sugar level readings, and the median for this is 7, for example, and we would like to test out if the median is indeed 7 here in this case. So we can check using the runs test. So this is a numerical data. Researcher would like to first categorize into two groups based on the cutoff. The cutoff is 7 here. Okay, so and that cutoff can be configured and can be taken any value that the researcher finds appropriate here. So that's my data, simple data, and then we take the median of 7. And after that, we create a binary sequence. So wherever the value is greater than 7, let's put plus, and wherever it is not greater, put a minus. So that can be simply taken or obtained by just checking if the value x is greater than the median, then plus, otherwise minus. So that is my binary sequence that for the data set that we have. Now we need to identify the runs here. So identify the number of runs from the the pattern, and that is 15 runs here. Now out of this we have to find out the number of positive runs and negative runs. So just sum it wherever the value is greater than the median, take that. So that would be n1 would be positive and n2 would be negative. So this is 21 and 19. So total number of observations is your 30. Now substitute those values n1 and n2, and then here also that's going to give you the mean of the distribution or the sample. And then again put the values here, and that's going to return the variance of the distribution. So that's 13.6 and 2.24. So now we have the mean and standard deviation. We can compute the z-score of the run data. Okay, so this is the number of runs, and then we substitute the mean of the run and standard deviation of the run to get the z-score. So that's my z-score here. Now this can be compared with the critical value. Let's say our critical value is 0.05, which is 5%. So get the critical value from the norm PPF, which is a standard normal distribution, and provide the alpha, and you get the critical values. And twice of that would be your p-value, like we discussed earlier in the t statistic as well. Now we plot the z-score on the x-axis, and the critical values are marked by the red line, and anything outside of it would be your rejection region. Similarly here also rejection region, but our test statistic is falling inside, so we will not be able to reject it, and so we go with the null hypothesis. So we cannot reject the null hypothesis, so we are failing to reject the null hypothesis. And what is the null hypothesis? It's saying the sample is a random pattern, which is to be taken as true. The sequence is indeed a random in this case. Okay, so that was the Python demo on runs test. I hope that illustration was simple enough. So we'll see you in the next video. Thanks for watching.